All right, gentlemen, very well done on your quizzes there. Remember, it's all good news. All good news. All right, let's dive on back in here and get into this next portion here, this next lesson. Okay. Now, we have people that are beginning to join us on YouTube here. Welcome to all of you. And Hanson, I want to encourage you there one more time as an audit student here. If you have any questions while we're going through the lecture here, you feel free to jump in and ask those. You can turn your mic on and ask them. You can type it in the chat box. You can use the raise your hand icon, whatever. And I'm also going to give you right quick my email address. If you have any questions after you leave us, feel free to drop me an email. And I promise you, I always return my email. So welcome, and I hope you enjoy your stay there. All right. Now, I told you guys earlier that in your role as an A+ technician, you may very well be managing, monitoring, and even configuring networks as well. That's very, very common for A+ technicians to sort of cross the boundaries there and perform those functions as well. Now, there's very specific requirements and rules that one should follow when you start setting up network addresses. Excuse me. We will take a look at your basic network stack. We will take a look at your required common communication ports and protocols. We will take a look here at some pretty detailed definitions of network configurations in general. Now, some of this we've already spoken about. So we're going to sort of be wrapping the bow up and summarizing some of the stuff that we've already talked about here. Now, connecting to the internet in general, there's several different ways. For the most part, and we looked at this same graphic here earlier in the network configuration, the SOHO kind of networks there. The local area network is the originating point where all of us get our access to the network in general and eventually the internet. I want you to understand, too, the basic framework and the infrastructure that has now grown to become the World Wide Web, the internet, all began with local telcos. All of the infrastructure, the wiring, the telephone lines that are buried underground that are hanging on the light pole or the telephone poles, we see them everywhere. That is the basic infrastructure that began the whole internet, the World Wide Web. You probably remember back, some of you may not, years ago, all of the every little community all across the country had their own little, oftentimes locally owned telephone company, telcos. Then they began to be merged into larger conglomerates here, and eventually the likes of AT&T and Verizon and all of these broadband network carriers began to gobble up all of these little tiny telcos that were spread out all over the world, all over the country. And then they consumed all of their in-place infrastructure. And you can still drive through just all the hills and dales of the country here. And way back when I was a young whippersnapper, if you wanted to get telephone service, you had to go down to the telephone company, which was usually some little block office building that was set up. And that's where all of the wired infrastructure terminated, in that was the telephone company. You can still see these little businesses and the old concrete block building that was the telephone company up in Blairsville, Georgia, where our little place is up there. The old concrete block building was, right on the outskirts of the downtown area. It's still there. And now it has been consumed and is the office of one of the internet service providers up there. But that's where all of the infrastructure, all the wiring that went out into the hills and dales, up and down all the streets, that's where it all terminated. And that's where all the switching equipment is for that local subspot there. Now, in large areas all over the world, there are these massive data centers, and they're called IXPs, Internet Exchange Points. And I got to visit one in I'm bound. I really can't reveal the location because I've got a non-disclosure agreement I'm operating under. I will tell you, it's one of the coolest things I've ever seen, and it is deep underground somewhere on the eastern seaboard. It's about as detailed as I'm going to get, but massive, massive tunnel, um, and just hundreds of thousands of wires of every sort you can imagine. Coax cable, thin net, thick net, fiber optic cable, RJ45, 8-wire twisted pair, 4-wire telephone cable, 2-wire telephone cable, all of it terminating in this massive, massive internet exchange point. And then inside this massive area, all of the internet service providers in the area, and in this area, there are about 3 or 4 dozen. Well, they've all got their cages set up with all their switching and their routing and their connectivity equipment there. And then that infrastructure then services outside all of their customers and all of their substations and subspots and so on. Somewhere along the line, inside of all public and private companies and individual homes, residential areas, there is a router modem device somewhere that has some type of connection to the internet service provider. Okay. Between the internet service provider and your home, there's an area called a demarcation point. And you guys can go outside and look on your home right now, your apartment, your home, your business. Hanging on the side of the building there, there'll be some plastic, usually hard plastic box where the cable company's cable terminates there, and then the inside your network, it goes through the wall, and that's where the handoff is, in essence, from your internal infrastructure to the outside world, to the World Wide Web. So all over the internet, the World Wide Web, you will see these internet exchange points, which is the termination area for all of the wiring and the connectivity of the equipment there that then services the entire community out and about. We find now that the infrastructure now has been upgraded in most residential areas, anyway, especially in large metropolitan areas. The infrastructure has now been upgraded to where it's either a combination of coax or a fiber. And there's some interesting connection types there. They call it fiber to the curb, where they'll run the high speed signal into the underground to like in a cul-de-sac, and then from the subspot there, it's coax cable to the individual homes. Well, they finally upgraded ours in our cul-de-sac. It's all fiber right into the home for everybody here. So the technology is being upgraded here and there and everywhere, and we're seeing lots now of this infusion into these wireless WiMAX networks there, the long distance, very powerful wireless networks as well. So, and even now with the implementation of the satellite, the low Earth orbit LEO, low Earth orbit satellite networks, Starlink, Elon Musk organization there. And there's about, I don't know, 4 or 5 of those kind of LEO networks all over the planet there. Very efficient, low Earth orbit. They're only about 600, 650 miles up, as opposed to your cable TV and satellite TV, which is 22, 23,000 miles up. So latency is less, coverage is better, quality is better, the signaling speed, unbelievable. But it all sort of terminates in our residence and our business with this type of configuration here. Okay. You have a modem, which is an abbreviation for modulator, demodulator. Now we find most of the modems are digital devices. Now it's pure digital data going across these network connections rather than doing the analog to digital, digital to analog conversion, that kind of thing. Because it's, digital lines now. Either coax cable or fiber optic cable, and it's pure binary digital data being transmitted rather than the old analog frequency modulation signal. There's still a lot of the hybrid networks hither and yon throughout the entire country, but a lot of it is beginning now to move towards the pure digital fiber optic cabling, that kind of thing. Now, each one of the devices inside of a network In addition to having their hardwired MAC address, which never changes, they are usually getting a logical IP address assigned to them. Now, usually by a server inside the network, it's called a DHCP server. That's Dynamic Host Configuration Protocol server. That is one of the common ports and protocols that I gave you guys that link to the document yesterday, the common ports document. You will absolutely need to memorize and know these communication ports, the protocols that operate over those, and you'll need to be able to recall it from memory because they ask lots of different questions about these things. DHCP is the one that is responsible for assigning your session level IP address. Now, the IP addresses as we know them today are along these lines right here. Okay. These guys here are, that's an IP address, Internet Protocol address. It is broken up into what we refer to as 4 different octets. Okay. Each of these guys is a combination of 8 binary bits. Now, currently, the IP version 4 address, as the computer knows it anyway, is 32 binary bits. And the combination of those 32 bits translated into what we understand as digit IP addresses. So very common, 192.168.5.15. Or if it's a large network like a, they call it a Class A private network, the address might be 10.11.9.15. And I'm talking about internal private network addresses. The outside network addresses are a different range of public IP addresses there. And when the Internet Engineering Task Force and the couple of other organizations, one called IANA, the Incorporation for Assigned Names and Numbers, they all decided what the whole schema was going to be. They says, all right, well, computers at the time anyway operated with 32-bit processors. So they said, we'll create a 32-bit address. And inside that address range, if you break it down to the numeric counterparts, there's 0.0.0.0 all the way up to 255.255.255.255. And within that network range there is somewhere in the neighborhood of 340 billion available addresses within that binary range there. Well, then they sort of cut that almost in half and says, we're going to dedicate these 3 ranges of addresses here as private network addresses that will only be used internal in networks. There's actually 5 ranges, but 3 major classes. And those will never be used to transmit data out over the public internet. These leftover ones are the ones that we're going to assign as public IP addresses. You'll find that most companies only have 1 and sometimes 2 public IP addresses that are assigned, or they call it leased to them. But there's an organization called ICANN, the Internet Corporation for Assigned Names and Numbers, and another organization called IANA, the Internet Assigned Names and Addresses, that they lease these public IP addresses, the guys that look like this, to a private company. And that's how all the traffic that goes out over the public internet sees this address. They never see these private addresses. Those are behind the firewall, behind the router, inside of a private company. Okay. And then there's a function that's performed by the router device here. It's called network address translation. We'll talk about that in more detail later on as well. But every appliance, every device inside of a network has both their MAC address, which never ever changes. It's hardwired right into the network adapter, but they also have a logical IP address that's assigned to them, usually by the DHCP server. And we'll talk about all of this in detail later on. Okay. The modem, the modulator demodulator device, is what does the handoff and the modulation of the signaling to send out over the internet connectivity, and the translation back to binary, which is the language that the computer reads or understands, and all that. Okay. The modem, the modulator demodulator device itself, is something that for the longest time was complete analog. All the data was being sent over existing telephone lines. Now, and then they had sort of an interim here. It's called a DSL, digital subscriber line modem. That was the modulator demodulator, because the telephone signaling was still coming in as analog data, and the internet companies found a way to transmit the internet connectivity on those same existing telephone lines. Those would plug into the DSL modem here, and the modem would split up the analog telephone signal, allow you to send that out to your attached telephone. And then the digital signal was sent out an Ethernet connection, this guy right here, to your computer. Okay. And then they upgraded these things to where you didn't have to wire it. It was also a wireless modem that looked like this guy here. Okay. So it did that analog to digital, digital to analog handoff there. There's actually 3 different versions of the digital DSL modem, and they were different speeds and different functionality. And again, it was sort of an interim when all of the signaling was coming in on, especially out in the hills and dales, where they didn't have coax cable or they didn't have fiber optic cable, but they had existing telephone lines. So they found a way to send the network signal down that line into this DSL modem and split it up between the telephone and the internet connection. ADSL was the first version of this. It unbelievably slow in, in looking at today's modern speeds. It was somewhere in the neighborhood of about 24 megabits per second download, and you never got that. You got 13, 15, something like that. And then the uplink speed was about a fourth of that. They promised or tried to promise about 12 megabits per second upload. You never got that. It was 3 to 6, something like that. And then another version of DSL was called symmetric DSL. That was where the download and the upload speeds were the same, still very slow. 24 megabits per second is really what you usually got. And then there's a third version of it called VDSL, very high speed digital subscriber line. And it was also the same, the symmetric, same upload and download speed. But the difference was how close you were to the actual substation. So if you wanted to get the VDSL signaling, you had to be able to basically throw a rock out your window and hit the telco substation. Okay. So that you had to be much closer to get that kind of speed. And in some cases, they would even give you 2 different lines to be able to get that speed there. That's what I had at our mountain home for years. And it just was not fast enough for me to even teach my classes online there, because, like I say, I'm pushing video, audio, and presentation here. Man, I did a happy dance when they finally installed first the coax, the cable modem, because it did give me the speed I needed. And a lot of folks are still working with the cable modem. The coax cable comes into the modem, and then you have RJ45 out of the modem. Pretty fast. These things give us a good speed, much better speed, of course, than the DSL or the analog modems for sure. And of course, the first time we saw this stuff was when people started getting their cable TV piped into their home. Okay. It utilized a pretty interesting operating system called DOCSIS, Data Over Cable Service Interface Specification. And the modem itself then was upgraded where it actually split up multiple signals. Not only did it deliver the internet signal and your telephone signal, but it also delivered sometimes hundreds of TV channels. And the cable box itself split that up and sent those signals to the different components inside your home. Then we started getting real high-speed connectivity with the implementation of these hybrid networks, coax to fiber, fiber to coax, that kind of thing. You see different versions of it here: fiber to the curb, full fiber to the premises or fiber to the home, FTTH, we see that. So very, very fast connectivity. The cable modem or the fiber optic modem itself usually had multiple interface ports on the back of it for RJ45 connections internal, these kind of things. It also had oftentimes either an analog phone or a digital phone plug in the back of it. Most of these guys also had some type of an optical connection in there for driving like TV channels, digital TV channels, that kind of thing, USB drives, that kind of thing. But now I tell you, into the full fiber to the premises or fiber to the home, fiber optic cable runs through the wall right into the fiber modem itself. So everything is extremely screaming high speed, no doubt about it. Okay. The optical network terminal, they call it ONT. That is the one that we have inside of the home now, and it again splits up all the signals: TV channels, security system channels, telephone channels, internet connectivity, all of it within that in that singular box. Here's what I was talking about with the LEO satellite connections there. Cool thing about the LEO networks is that it is a grid of satellites rather than, a singular satellite with multiple transponders. If any of you guys have ever had, and I know you probably have in the past, I certainly have, satellite TV signal, terrible reception. I mean, a flock of birds flies over you, you lose your signal. Or, wind blows up a little bit, you lose the signal. And the geostationary satellites tend to drift badly. And you are communicating directly line of sight with a singular transponder on the satellite itself. The LEO satellites, pretty interesting. They Skylink, for instance, or SpaceLink, or whatever Musk Skylink, I believe it's called. It is when they complete it, it will be a grid of 4,273 total satellites in a grid type network. The alignment on the antenna is very easy to do. It's self-alignment sort of thing. Each of the satellites in that network they're huge. They're, about like so, but they're autonomous. They're, of course, solar powered. They speak with one another, and it's a mesh type of network. So when you set your antenna up, you may be getting a simultaneous signal from up to 4 different satellites. So it's got that redundancy baked into the grid. Plus, it's only 620, 650 miles up, as opposed to 23,000 miles up above the surface of the Earth. So really good reception. I taught a class for a military up at Tennessee, actually Clarksville, Tennessee, on the border of Tennessee and Kentucky up there, at the Army, or at the base up there where they do the technology upgrades and the maintenance on the Black Hawk and the Apache helicopters. Very cool environment. But the data center that we were in was a SCIF, and we were not allowed to hook into their network. But the major who actually arranged the class up there bought in his Skylink device. We had it in the classroom. We went up on top. There's a 3-story hangar building there. Went up on top. Very easy alignment on the antenna. And I mean, it was screaming demon speed. We didn't drop the network not one time. I had 31 students in the class, and everybody had screaming connectivity. It was awesome. Those things are expensive, though. I tell you, some of those things are, $300-400 a month based on the functions that you have there. The WISP internet service provider, that's point-to-point stuff I was talking about, the WiMAX point-to-point kind of networks. That is something that we're starting to see, especially in large flat areas of the country where they don't have to go over, under, around, and through mountains. So we see that quite a bit. The geostationary satellites, there's a lot of latency there, a lot of drift on the satellite, a lot of reconnects, that kind of thing, and large degree of dropped connections there too. Now we are beginning to see, and I think I like the way this is set up. How does T-Mobile's new satellite system work? Similar to Starlink? Very similar, Kevin. It is same kind of thing. And I think they're even leasing some space on a couple of the other grid low Earth orbit networks there. So I think they're tapping into some of that. And I don't know which ones, but it's the same concept. It's LEO type of satellites. And the cool thing is what I was about to say here. The combination of the satellite grids, the LEO satellite grids, and the land-based cellular towers is really starting to pay off, especially with the 4G LTE and the 5G, fourth generation, fifth generation cellular connections. So it's a hybrid mix. You've got land-based wireless connectivity, and then satellite jump off and hand off on the like the Verizon and the T-Mobile and all of their other grid type of networks there. So great high-speed connectivity. These guys have these massive multiple input, multiple output arrays of antennas. And you got best of both worlds. You got satellite connectivity, you got land-based cellular connectivity, and the Wi-Fi connectivity point-to-point traffic there as well. So it's a nice hybrid combination. That's why I'm telling you, we're going to start seeing more and more, and I already have in some parts of the country. They're ditching their hardwired network connections. They're going with these 5G hotspots, and that's their primary internet connection because it's a combination of all of those. It's the land-based cellular towers, it's the point-to-point Wi-Fi connectivity, it's the hybrid satellite grid there as well. So you have roaming through the network, fixed access, and all of the above. And all of the mobile appliances, for instance, the mobile phones, prior to the implementation of the 4G long-term evolution, 4G LTE, the old GSM phones there, they all required the SIM cards, but the CDMA ones did not, even though most of them had them anyway, but it wasn't required for communication. Now they're all GSM world type phones, and they all are using SIM cards, either the physical card or the eSIM, those kind of things. And that's everything from 4G LTE and forward. So very, very strong propagation of the signals. And the subscriber identity module, the SIM card itself, tracks not only the user, the subscriber to the service, but the device itself. And all that information is passed around throughout the network as you're roaming throughout there. Okay. Now, probably the most direct connect appliance that we have in these networks is this guy right here, your router. That is what it actually logically moves data through a network. And the routers, the modern routers, man, this is some of the most intelligent pieces of equipment I've ever encountered in my life. And say if you have a large network, you may have dozens of routers that all constantly communicate with one another's. They constantly advertise what their routing tables contain. In the routing table, it has all of the connectivity information for every point to every other point in the network. And this is the best route that we go through here. And all the routers now, they not only monitor for all of the other routers making suggestions on changing routes, but they also advertise their best effort routing to all the other routers as well. So they all communicate dynamically, and they make these nanosecond decisions. Let's say if we have, 3 dozen routers in an autonomous network, they all are pretty much aware of what the best route, the most efficient route from each point to each other point throughout the entire network is. But let's say one of the routers over here in this corner of the network recognizes, well, I'm getting a bottleneck of traffic because too many people are trying to communicate with the systems behind me. So we may need to go a different route for more efficient routing of the traffic. And they all make those decisions dynamically. The routers themselves establish a logical movement of data through the network rather than a physical point-to-point movement through the network. And they evaluate all kinds of metrics. What is a lot of them use what they call open shortest path first, OSPF. What is the least number of hops that I need to make to get from here to here? and each of those hops is a router. Okay. Or they also evaluate bottlenecks, traffic, too much traffic into one router, well, they may route around that and more efficient movement to the final destination. Or if one router is experiencing a problem, a whole bunch of data frames for whatever reason, well, the other routers say, well, we're getting a lot of discarded data frames over here. We need to go this route. And again, the cool thing is they make those decisions at the nanosecond level and dynamically change routes. Now, you have to understand too, people tend to think that when I establish a connection from one point to another point, that all the data is just a constant stream. Not at all. All of that data stream is broken up into what we call frames or data packets, small digestible chunks of data. And each of those frames, if I'm sending this video stream, this audio stream, you would get the impression watching and listening to it that we are dynamically connected and it's all just one constant stream going the same path through a network. That's not at all the case. There's no telling how many different jumping off points are between the go-to servers and you guys receiving this stuff in your home networks. Okay? Could be dozens, could be 25, 28, 30 different routers that it has to go through. Well, those things are constantly updating and changing the routes that each of those data frames may go. Well, each of those packets is assigned on my end, on the go-to end, a sequence number. So if one packet goes a different route than the other, it may be received on your end out of sequence. So the system then reassembles those things in the proper sequence and then plays it back to your systems, you see. And that's all data operates in that same mode. Each individual data frame and packet has a sequence number that's utilized to reassemble that data stream on your end before it's played back through whatever package you're playing it back through, you see. So, and if you start thinking about that, that's a pretty amazing disassembly and reassembly of all of the data streams as it flows out through all the network. Okay. So the router is the component that connects your local area network to a wide area network connection and then to the internet, which is the largest wide area network on the planet. And it makes all of these routing decisions dynamically based upon that establishment of these logical networks or subnetworks inside of the larger World Wide Web. Again, these things are just amazing, amazing devices there in that they do all this stuff at the nanosecond level. Firewall is another network component that everybody's heard of. Sometimes people don't fully understand what firewalls do, but they are sort of a gatekeeper, if you will. It is oftentimes a dedicated server or appliance, a piece of hardware. That's the firewall. Oftentimes, however, it is software that is built into other services and systems. Sometimes it's built into the router device itself. The one that I have here in my home has a firewall built into the router gateway appliance. Excuse me. They are programmed with what is referred to as an ACL, an access control list. And it's basically you're setting up rules or filters, as it were, that are processed. Every time a data frame is introduced, it basically goes down this list of rules or filters. And conceptually, it says, allow this, or allow this, or allow this, or allow this, but deny everything else. If it hits on a rule that is satisfied, well, it goes on through it, doesn't even check the rest of the rules primarily. That's called whitelisting or implicit deny, meaning that unless I specifically or explicitly define a rule that can be satisfied by this data frame, is it from this IP address? Is it from this domain? Is it from this user? So allow that or allow that or allow that. But if none of those are satisfied, deny it, dump it. Don't allow it to get through. That's how most firewalls work. Actually, that's how most of your network security equipment works, with that whitelisting, implicit deny type mode. Okay. So A very powerful device, and the later ones, the newest ones, call them next generation firewalls, they can do some much more sophisticated analysis of data frames rather than that just processing the access control list. Okay? So they're a lot more intelligent too. Everybody needs to run a firewall. You need to have a firewall at the network perimeter, and you need to be running firewalls on each host computer inside of a network as well. In the security class, we teach a concept called zero trust, always verify. Used to in the old days, if you had a user ID and password that allowed you to log into the network, you were assumed to be a trusted entity. Not anymore. You want to check those credentials and to check that access at every step along the way there. Certainly at the network perimeter, but on each individual host machine as well. Okay. So there we talked over some of your connectivity types. We talked the concept of the modem. We talked about cable modems, the new fiber optic connectivity now. We talked about the different access points. We talked about your wired and your wireless connectivity, and now the hybrid versions of that, and a couple of the equipment types, your wireless access point, your routers, your firewall. I'll tell you another thing that all of the modern systems now as well, and I'm talking about routers, switches, firewalls. There's another system called an intrusion detection and an intrusion prevention system, proxy servers. All of those systems nowadays are supplemented with some type of machine learning interface, almost artificial intelligence, actually a sublayer of artificial intelligence. So they make much more efficient decisions. They truly do learn over a period of time and begin to build a security profile of your organization and get much, much better at making good quality decisions. Now, here's something you guys need to memorize: this TCP/IP network stack. 4-layer module. The old version of this network stack was a 7-layer module. It's called the OSI network module, Open Systems Interconnect. This is one that was actually created originally by the Department of Defense. It's called the TCP/IP model. That is Transmission Control Protocol / Internet Protocol. It breaks it down into 4 specific layers, if you will. And picture this and another one sitting right beside it that controls the communication between 2 host computer systems. The communication begins at the application layer. The request is then passed down to the transport layer, which decides which communication port and the type of communication session you're establishing. Passes on down to the internet layer, which looks at your IP addresses, the source and the target IP address. Goes down on to the network interface, the link layer, which says, oh, okay, here's the internet IP address and here's the MAC address. So hand it off to the network adapter and then break that information down to the binary digital data, send it across the network connection to the link layer on the other side, and then unstack it as it goes back up and presented to the application on the target side. Now, some of the applications that we talk about here, and we'll look at them in more detail as the week goes along. I spoke about DHCP, Dynamic Host Configuration Protocol. There's also domain name services, DNS. You guys may be familiar with FTP, File Transfer Protocol. There's Simple Mail Transport Protocol. There is HTTP, which is your Hypertext Transport Protocol, communicating with websites. Okay. Now, there are what we call common ports, and I gave you guys the link to that document yesterday. You need to memorize those because the common ports and the software protocols that run over those are the ones you're going to get questioned about on your certification exam. Okay, so you got to know what those are. And in that common ports area, that's usually the ports between port 1 all the way up to port 1024. And then there's a couple beyond that that you need to be aware of as well. But those are the ones in the middle of those is DNS, DHCP, file transfer, HTTP, your boot protocols, your server message block, your lightweight directory access protocol, all of the ones that we utilize within that common ports range, they call it. You guys need to know those because they throw all kind of questions at you on your exam. And just assume that not only do you know what the communication port is, but what software runs over it. Okay. For FTP, that is port 21, Telnet port 23, HTTP port 80, HTTPS port 443. So you got to know that association between those software protocols and the communication ports. You get a bunch of questions along those lines, so take that to heart. So this is the network model here. Now I mentioned to you guys earlier as well, this ARC cache, this guy right here. Okay. Now the ARC cache, remember, address resolution protocol, that sort of hovers between, in the network model, your internet layer and the link layer, the data link layer, we call it. It associates your physical MAC address, which is tied to your network adapter. So the MAC address is here, okay? The IP address is assigned up here. The data link layer and the ARC cache in the middle associates those two. Remember, the MAC address never changes. It is consistent. The IP address may very well change session to session to session. So this ARC cache is dynamically updated when you log in and get a new IP address. It says, oh, okay, here's the MAC address. Here's the new logical IP address for this session. So you always have to remember that. Okay. And they'll ask you questions about that on your exam too. So make sure you take all that to heart. Now, here's some fun. You guys ready to have a little bit of fun? I'm going to show you how we do the translation between binary to decimal. Okay. Let me pull this down here right quick. Well, we'll use all that later too. So, right now, a couple of things I'm going to highlight here for you, and they will all begin to make sense here shortly. I told you we had the 32-bit binary address that was originally created by the engineering task force and the IEEE organization. Binary is a base 2 numeric system. Okay. So in order to do a binary to decimal translation, we need to understand that binary numeric system. Now, remember I told you we've got 32 binary bits. So we break those down into 4 different 8-bit octets. And the teams chose 8 bits because 8 bits equals 1 character or 1 byte on a computer system. So it just made logical sense. And the old computer registers were operating in 8 binary bits each as well. So each of those values, those 8 binary bits, we associate with a numeric placeholder value. Now, all numeric systems, doesn't matter what they are, base 2, base 10, base 16, hexadecimal, they all begin with a value of 1. Now, some mathematicians, and they've changed their evil ways over the years, they say, well, no, all numeric systems begin with 0. But pretty much a mathematical consensus, especially in the physical world, physics, 0 is not a real number. So all numeric systems begin with a value of 1. Now, I chose these values here because we're talking about 8 binary bits. Okay. So moving from right to left, this is 2 to the first power, binary, 2 to the second power, 2 to the third power, and so on, all the way up to 2 to the 7th power here. Okay. Now, if I take those 8 binary bits and I say my first octet of my binary address, let's say is 1, 1, 0, 1, 0, 0, 0, 1. Now, for me to translate that binary address, this right here, to its decimal equivalent, what I need to do, and you guys break out your calculators here, I need to, everywhere I have a true or a one value in the binary, I need to add its equivalent placeholder value. These placeholder values never change. They're always constant. Okay. So in this case, and you guys whip out your calculator, I would add 128 plus 64. I don't add 0 or 32 because it's 0. So 128 plus 64 plus 16 plus 1. Those are the
209.
placeholder values. Okay. What is that amount? What's that value?
209.
All right. Anybody concur on that? 209?
Yes.
Yeah. That's how I do binary to decimal translation. Okay. Now let's say that I do this. Okay. What is the decimal equivalent of that?
193.
There you go. That's how you do binary to decimal translation. So if I have 32 binary bits, which is how the computer knows my address, I first carve it up into those 4 octets, we call it, associate each of those octets with these constant placeholders based on powers of 2. Thus, I give the output. Okay. That's how you do binary to decimal text, decimal translation. Okay. Now, they are probably on your exam not going to ask you any questions and have you do binary to decimal translation, but that's how you relate the binary 32-bit address to what we all see nowadays as this guy right here. Okay, by doing that binary to decimal translation. So we human critters, we know our IP address like this. The computer knows it like this. And that's IP version 4. Now, we are seeing more and more now representation of our addresses, and they call it classless inter-domain routing. The reason being, I was telling you guys when they first came up with this whole addressing scheme, they says, all right, 32 binary bits, that ought to be enough addresses for everybody on the planet. Well, they carved it in half, and then they missed the boat. They had no idea that this little guy right here was coming down the pipe. Okay. Everybody on the planet has a mobile phone. Just about everybody on the planet, in civilized countries anyway, they got 1, 2 computers, a couple of mobile phones, maybe a tablet device, a smart TV, a security system. Every one of those things has to have an IP address to communicate out of the public internet. We are literally running out of public IP addresses in order to lease to companies and to provide those for individuals that need IP addresses for all their devices. So that sort of blows the class-based routing function out of the water. Now they have come up with this new scheme, and this is just a placeholder too, by the way. It's called classless interdomain routing. You will see IP addresses listed like so: /24, /26, /32, /16. What that tells me, and this number that is trailing after these guys here, and you'll see it listed just like that, the IP address and then /24. That tells me that the first 24 binary bits is the network address, leaving the last 8 bits that I can utilize to calculate host addresses inside that network address. Okay. That also goes to where we call it a subnet mask. And I'll show you how all that works here in just a moment as well. But if this happens to be /26, that says, well, the first 26 binary bits is what I'm using as the network address, leaving only the last 6 binary bits that I can calculate addresses, host addresses within that network address. Okay. So the subnet mask changes, and it gets away from that basic class of A, class B, class C private network addressing there. And we're starting to see that more and more. Now, what they're doing there is preparing to go to the next version of IP addressing, which is going to be called IPv6. We'll get into that more later as well. Now, another couple of things about the private IP addressing here I want to show you guys. Let me pull this up over here. Well, no, never mind. I've got it on the slide here. There we go. This guy right here is what I was looking for. This is a class A private IP address. They begin with 10.0.0.0. The CIDR notation, we call it the classless interdomain routing version of that, is /8, telling me that only this first octet, or the first part of the address, is the network portion of the address, leaving the last 3 octets that allow me to configure host addresses within this network address. Okay, those are called Class A networks, very large networks. And actually, if you look at it, it is 256 times 256 times 256, are almost 17 million available host addresses within each of these networks. Okay, /8. Just the first 8 binary bits is the network address. The Class B networks /16 masks out the first 2 portions or octets. That is the network address, leaving the last 2 for me to be able to calculate host addresses. Okay, those guys allow me to create 65,534 host addresses. And then we get to the subnet mask. This subnet mask of 255.255, if I turn on all of the binary bits in one of the octets, it adds up to a value of 255. If I turn on 128, 64, 32, 16, 8421, that's 255 total. And I use that to mask out, okay, the first 2 octets of that as the network address. That is the same concept as this /16. And then the most often one that we see is called a Class C private network. It masks out the first 3 octets, and that is the network address. Same thing as /24, leaving only the last 8 binary bits, where I can come up with a total of 256 available host addresses. And it's because it starts at 0 and goes 255. Okay. So that is class-based interdomain routing and classless interdomain routing. This subnet mask is the same thing as /8. This subnet mask is the same thing as 16. And this subnet mask is the same thing as /24. Here's how it works. Let's pull the old guy up here again. Here's the way it works. Let's say if my IP address is 192.168.5.15. I want to communicate with a computer whose address is 192.168.5.123. Okay. Now, that is a Class C network. In that Class C network, the subnet mask is 255.255.255.0. If I'm using the classless interdomain, it would be /24. Forgot my dot there. What I would do is I will take this subnet mask and overlay it on both the source and the target network address. And the subnet mask says, I'm masking out the first 3 octets as the network address. Are they the same? Yes, they are. So I know that is somebody within my same network. I don't have to route it out over the public internet. I just the bump back to the switch and says, oh, okay, that computer's plugged into port 5 over here. So it's in my same network. Now, if I were doing this, same thing. I'm masking out the first 3 octets as the network address. So I mask out those with that subnet mask and ask the same question. Are they identical? No, they are not. So that has to be handed off to the router, and it finds based on its routing tables where this computer actually lives, what network it actually belongs to, because it's not mine, because those first 3 octets of the network address are not identical. You see? So that's how the subnet mask is utilized to make that decision. Now, that decision is referred to as network address translation. The router gateway device typically makes that decision, and that's usually the router that's closest to your computer. So I create a communication packet. I know my IP address. I know the IP address of the target I want to talk to. That hits the gateway box. It does that overlay of the subnet mask, makes the decision, is it my internal network or is it a different network? And then it decides to route that traffic out of my network or my subnet, or to hand it back to my switch so that it can be delivered locally. And if I'm going outside of my network, it also masks my private IP address, assigns it to an instant of whatever my company's public IP address is. So it looks like the same IP address coming from my router, and it keeps my private IP address private. So the network address translation service does that, and it never exposes my IP address out over the public internet. Now, I told you guys, I can have my DHCP server dynamically assign addresses, or I can do it manually. Now, I'm not sure if I mentioned to you guys, I have a learning disability. I'm dyslexic. You want to see somebody make a mess? Have me go in and require that I manually configure 15 computer systems with all this stuff. If I'm doing it manually, I decide what IP address I'm going to assign to the computer. Okay. I also decide, so I give it the IP address here. Oh, let's try that. I decide what IP address I'm going to assign. I have to tell it and key in what the subnet mask is for this network. I give it the IP address of the gateway device, which is usually the router that's closest to me right here. And I have to key in the same IP address of the DNS server. Okay. Now you see those are both the same. So that router gateway device usually is the same device. But I have to manually key all this stuff in. Or my preference would be to let set this in dynamic mode by pulling this drop down list box right here and let the DHCP server handle all of that for me. So it dynamically assigns IP addresses when somebody logs in to get their new logical IP address.
Are the subnets always the 255, 255, 255?
The subnet mask, it is always one or the other. It's according to the size network. If you're a Class C small network, it's always 255, 255, 2550. If it's the medium-sized network, a Class B network, it's always 255, 25500. And if it's a Class A super large network, like your ISP is a very large network, the subnet mask is always 255000. Yes.
Okay.
So
All
those
right.
are always consistent, Kevin, based on the size network you're actually working with.
Okay.
Yeah. And remember that classless interdomain routing concept too is being used more and more. So it's /24 is the class C network, /16 is the 255.255.0.0 class B network, and /8 is the 255.0.0.0 class A type networks. So those are always consistent as well. Okay. Now the dynamic host configuration protocol, excuse me, is the software and the service. And by the way, we're going to go past the lunch break here a little bit, but that's okay. This is the service that dynamically can assign my IP addresses, and that's my preference. Okay. Now there is a specialized IP address that is automatically assigned. You have to remember this because you will get a question on it on your exam. Okay. There's an IP address referred to as a PIPA, automatic private IP addressing. There's only one reason a system gets an APIPA address, and that's because when you go to log into your session, for some reason, and it could be a number of reasons, you cannot make contact with the DHCP server to get your IP address. So Windows automatically will assign this APIPA address, automatic private IP addressing. Now it will allow you, excuse me, I got phlegm in throat, don't know why. It will assign this address so that you can communicate with local people inside your same network, inside your network segment. So if somebody calls you up and says, you know, I just logged into the network, I can talk to the people in the same department, but I can't communicate with HR. I can't communicate out over the public internet. Well, there's a command that I can run or have them run on the computers called ipconfig. We'll actually look at that command later on. But it will show them or me, if I'm running it, what their IP address is. If that IP address begins with 169.254, that's an APIPA address, automatic private IP address. Windows assigns that automatically so you can get a network session, but you can't communicate outside of your particular network subsegment. And the only reason that occurs is because something along the way has broken the link so that when your computer tries to log into a session, it cannot make contact or request an IP address from the DHCP server. And that's the only reason. Okay. You will get a question about an APIPA address on your exam. Remember, if somebody has an IP address that begins with 169.254, for whatever reason, they cannot contact their DHCP server. So they're not available to get their automatic private or IP address assigned. Okay. So remember that. You will get a question about it on your exam. Okay. And the IP config command will show that to us. I'll show you what it looks like later on. All of your routers, your router devices have a management console. We talked about that earlier. Most of them, you can dial it up. If you know the IP address of the router, you can just dial it up without having to manually connect to it. But that's where I go in and configure things like, do I want it to be the DHCP and the DNS server? Usually it is, especially in small networks. Do I want it to set up to be a static or a dynamic IP addressing? Okay. So there's a couple of different things that I certainly want to go in and reconfigure on those on that interface. We'll talk a bit more about some of that stuff later on. Absolutely, you want to go in and change the administrative password. Okay, harden that device. Okay. Now, let me see right quick here. I think we're about done with this. Now I've got a good bit more. So I'll tell you what we're going to do. We're going to go ahead and take our lunch break right now. I'm going to set your timer up for an hour on the lunch break. And then, because I don't want to get part of the way in this and go way, way past the lunch break. So we'll finish this up after we get back from lunch. Anybody have any questions here before we go ahead and set your timer on the lunch break and go get us a bite to eat? Anybody? All right, gents, y'all enjoy your lunch break. Be safe. And you folks on the on YouTube, I'm about to sever this connection. We will be back online on YouTube later on this afternoon. So please feel free to jump in and join us then. You guys have a good lunch, be safe, and I will see you guys after.